can start, I think. Okay, so welcome back to the afternoon session. So we have done with Bassi theorem. So we hope I try to clarify the way in which quantum world, the world of nature is non-local. So when you speak about non-locality, then you would like to open the door to science fiction things like jumping from one place to the other instantly or do these kind of things. Now we see that the answer is no. Non-locality is a tricky business, non-locality. And in particular, it doesn't allow for signaling. So there is perhaps the theorem is a big theorem. Calling it a theorem is a big name, nothing. Wouldn't call it a theorem, it's just a few line of calculation to show that although you have non-locality, you cannot use it for sending information after the receiver. How does the proof go? It's always the same story. Suppose that you have Alice and Bob, two people that would like to use entangled to communicate, so they share an entangled state. And I hope you are familiar with density matrices. Density matrices in quantum mechanics, I hope you are familiar. If not, it's just the wave function. If you're not so much familiar, it's the quantum state of the system, which can be entangled. And then, what happens? So again, a bit of math is necessary in order to understand. Suppose that Alice performs a measurement of some observable A, and then to understand it, so to encode mathematically the effect of the measurement, we need the eigenprojectors, P-A-N, of the observer. So Alice makes a measurement of some observable A. Then what happens on both sides? On both sides, you have here, I don't know if you can recognize that, but it's the collapse of the wave function. It is mathematically expressed. In the numerator, the state is multiplied by the projector. The projector projects, no? The superposition to one of the two possibilities. So the numerator is just a projector that collapses the wave function. The denominator here you normalize back to 1. So the denominator is a normalization factor. And then Bob doesn't know the outcome of Alice's experiment. And so you have to average over all possibilities. With the correct probabilities, the Bob will. No? This is, again, if you're not familiar with the density matrix formalism, just take it. This is just a way to express the Born rule, the probability of finding outcomes. You cancel this with this, and you have this simple expression. So this is the state that Bob has. So you have to think that the situation is just that there is a source in the middle of entangled particles. One goes to the left, one goes to my left. One goes to the right, just with some rate. It goes. Then Alice makes measurements. The state is affected by the collapse of the wave function, and so Bob collects particles in a state which, in principle, has been modified by Alice's measurement. And the question is, can Bob understand which type of measurement Alice made in a superluminal way? In a subluminal way? The answer is very easy. Bob makes a phone call to Alice. Look, what did you do? It's very easy, subluminal. The point is superluminal. Can Bob understand if and what Alice did? Well, the answer is no. It's no signal in theorem. Again, I just show you the proof. You see, it's simple math. So just to give you an idea, if you don't understand or if you understand, it's trivial at the end of the day. What does it mean? So the statement, can Bob understand what Alice did? What does it mean quantum mechanically? It means that Bob does some measurement, because in quantum mechanics you do either evolution of measurements. Bob wants to measure, to see. So Bob does some measurements of some type in order to understand from the statistics of the measurement, in order to unravel Alice's measurement. That's why it's written here. So now we are computing in the state that changed, the state. So this is, where is it? So this is rho prime. Prime means changed after Alice. So you take the state rho prime, and then this is again the Born rule. This is basically. So So this is the statistics of outcomes, quantum probabilities, nothing more. Just if you are not familiar, just longer expression, but it's quantum probability. So the quantum expectation of Bob measuring some observable O. Well, then I don't know if I want to go through the math. So basically here I plug for rho prime, I plug the expression of the previous slide. I do some mathematical tricks, and the one that I want to highlight is, where is it? Here. So, sorry if I go through the details, but because there is a physical meaning behind it. So this is a projection operator, which by the cyclicity of the trace you can bring on the other side, and because of the form, the operator PA, the projector operator for Alice, commutes with the observable of Bob. So because of commutation, you can bring it here. The projector, because it's a PA, projector operator of A, it commutes with the operation for Bob. So you can, so basically this thing here, it goes cyclicity, commutativity, goes here. Then since it is so you get a square. Since the projector, the square is equal to itself, then it sums to 1, whatever, and I don't want to go, you can read it. And you see that the bottom line is that the statistics of Bob for whatever observable after Alice made the measurement is the same as the statistics before Alice makes the measurement. So the bottom line is that the statistics, in quantum mechanics, the statistics is physics. The statistics is independent of whether Alice makes or doesn't make a measurement and whatever type of measurement. Whatever Alice does, Bob cannot unravel. So these are the quantum rules of doing physics, either unitary evolution or measurements, and so also with unitary evolution nothing changes, that is more trivial to see. And so the bottom line is that Alice and Bob cannot communicate using entanglement. They can do other things, you will see now. And so there is the no signal condition. So, a few comments here. So the first comment is that non-locality, there is a difference between non-locality and signaling. And the difference is the one I told you before. Two events can be non-local correlated because they pop out of nothing. Again, so even simpler than before. Suppose that in the two opposite sides of the universe, there are instantaneous flashes. Random, but when it flashes in some point, also in the other part, they flash. That is a non-local effect. Because they are correlated. They are correlated at a distance instantly. But there is no transfer of information. There is no signal that goes from one thing to the other. This is in standard quantum mechanics something similar. There are non-local correlations. When something happens here, there is instantly something else correlated over there, but there is no transfer of information, or transfer of energy, or transfer of matter. That's the no signal condition. So, in this sense, there is no direct violation with special relativity. It's not that physics, so for me, I told you before my point of view, but that's personal. Now I'm talking about the standard accepted knowledge. I'm talking. There is no breaking down of relativity and the tentative of putting together quantum mechanics and relativity. In fact, we have part of the theory. Now, first comment. Second comment about this commutativity here. Probably you don't recognize it. I don't know, have you done quantum field theory, to which level, I don't know. Have you heard about the microcausality condition in quantum field theory? Yes? No? Okay, so then it's informal. So when so it depends on the level in which the course on quantum field theory is presented. You can do it in several ways. But one of the key elements of quantum field theory is the microcausality condition. The microcausality condition is taken in the language, now I'm speaking not the language of quantum information, quantum mechanics, but the language of particle physics, of field theories. The microcausality is the condition of locality, not the bad locality I'm talking about. It's the locality of signaling, the locality of this theory, the no signaling. The microcausality condition tells that space-like separated observables commute. So when you have the fields of quantitative theory, at space-like separated points, the field should commute. And this is exactly in the language of quantum mechanics where you have this here. Now you have, it's not fields, you talk about observables, but in quantum theory the observables are made of fields. So if you have the observable of A, so the field around A, the quantum field around B, and the observable of B, the field around B, they should commute. So why is microcausality condition a locality condition? Usually you don't find it. It's given for granted, but you don't find it in textbooks in quantitative theory. Typically, this is the reason. Commutativity, everything is mathematics, it's obvious. The only real requirement in this step, so the fact that you use the cyclicity of the trace is a mathematical property, it's not a requirement. That's a bonus that mathematics gives you. In all this proof, the only requirement that you make is the commutativity, is this arrow here, is the commutativity between the observables of Alice and the observables of Angelo that are space-like separated. If they commute, then you have the no signaling theorem. So basically, the no signaling theorem is strongly connected to the microcausality condition of quantum field theory. And the microcausality condition in quantum field theory is important because it's one of the pieces of the spin statistic theorem. No? The fact that the statistics goes to the spin, that fermions should be quantized, half integer fields should be quantized as fermions, and integer fields should be quantized as bosons. Why is that? Spin statistic theorem, and also the microcausality condition enters. So we are talking about the foundations of, not only of quantum mechanics, but also of the mathematical foundations of quantum theory. But there is something else I want to tell you. So, you can say we are safe with R. So quantum mechanics is a good relativistic theory. I mean, in the relativistic version. The equation is not relativistic, you replace the Dirac equation. So you say quantum mechanics is okay with relativity. Well, yes and no. Because the question is, why is all this working? I go back. So why is the proof working? So there are many, of course, there are many reasons why it works, but now I want to highlight one thing. It works because if Alice makes a measurement, the state of Bob is the one we can hear. Or precisely, so if Alice makes a measurement, Bob's state changes in this way. So the state of Bob changes. The state of Bob. Because if you have entanglement, it's one state. If Alice makes a measure, the wave function collapses. So the state changes also for Bob. So Alice changes the state. But in a way, and that's the change, but in a way, read your slide, in such a way that Bobs cannot unravel, cannot understand that it changed. It's like, for example, I don't know, it's like scrambling a random sequence. So it's a new random sequence, but it's always random. You don't see any difference because for you it's still random, something like this. But the question is, well, why then Alice? So the measurement changes the state to this one. So before it was just this was the initial state. After Alice's measurement, the state is this one, it's different. But why is this one? So it's not just any different state, it's a different state, but which cannot be distinguished from the other one. Well, the answer is in the middle. The answer is, so this is von Neumann collapse and the Bohr rule. If you think it's something rather surprising that it doesn't have an explanation. So collapse, so this is the von Neumann collapse. Collapse, normalization, and the two cancel. So the Bohr rule, no, standard quantum mechanics, the Bohr rule is the square modulus of the collapsed state before normalization, right? It's the same number. The number that you use to normalize the state with the collapse is the number that gives you the Born rule. So, precisely because the probability rule of quantum mechanics is the Born rule, that you have this cancellation over here, this mathematical cancellation that brings you to this state that is indistinguishable from the original state, from the experimental point of view. If you formulate a quantum theory where everything is a standard quantum mechanics, except for the Born rule, that is slightly different, then you could do superluminal signaling. And that's, at the moment, it's a coincidence of quantum mechanics, which doesn't have an explanation. Quantum mechanics, because of entanglement, allows for non-locality, but because the measurements are not controllable, are stochastic, generally stochastic, and that's not sufficient that they are stochastic, but they are distributed in a very unique way with the Born rule by magic. This is by magic, because these are two entirely different things. This is a probability rule. This is a statistical thing. This is a dynamical thing. Here you have to remember dynamics, dynamos, no, I'm not an expert in Greek, probably you're more expert than me, is a change, how you describe it changes. So this is how the state changes because of something. So this is dynamics, this is the wave function, whether in a mathematical way, because the wave function is only a mathematical tool, it's not real, the collapse is the same, the collapse is not real, I don't want to enter into this, but if the wave function of the density matrix is the state of the system, the collapse of the wave function changes the wave function, and the world changes, it's dynamics. Any changes in a way simple, trivial, right or wrong, it's dynamics. So this is a dynamical effect, the collapse of the wave function. This is a statistical property, the probability of collapse. The two things perfectly match each other with a different collapse rule, if you wish, with a different probability rule. You could allow for superluminal signaling. And that, of course, the history of physics has taught us that in nature coincidence basically never exists. If there are coincidences, there is an explanation. We don't have that explanation. So I leave it here for your approval. Okay, so one effect of so now we play around with non-locality. We cannot do superluminal signaling. So no science fiction, no Star Trek probably was famous also here. Star Trek, no, was it famous? You're young, probably don't know. You know Star Trek, the TV series. Have you heard of it? Okay, so because you're young. So teleportation. So teleportation in the form of Star Trek is not possible. No, it's clear because it violates mass conservation. It violates any possible rule of physics that something disappears here and appears elsewhere. You are violating the conservation of mass, the local conservation. Well, you even global, because at some point you can. So that's not possible. But so the name is the name is not proper, but some form of teleportation you can do in quantum mechanics. Now we will understand. It's called quantum. So first, just the introduction of the Bell states. The Bell states is basically just a basis, no? It's here. So if you have one spin, now I'm slowly moving to the language of qubits that Vahid introduced in the previous lecture. So if you have a spin, you have just 2 degrees of freedom, 0, 0, and 1, or spin up and spin down, or plus and minus, the usual thing. If you have 2 spins, then you have 4 possibilities, 4 possible basis states, 0, 0, 0, 1, 1, 0, 1, 1. It's like a qubit. Now you can think of qubit instead of spins, nothing changed. And then this is the computational basis for quantum computation. So this is a basis of state. Another famous and interesting basis, because it's a rectangular state, is the basis of Bell states. This is how it is defined. It's just from the mathematical point of view, it's just another, instead of taking this basis, you take another basis in the Hilbert space, in this 4-dimensional Hilbert space, nothing changes. The beauty of the Bell states is that they are nice entangled. So all these states are entangled, and this you see that there is not the singlet does not 0, 1 plus. Oh no, here it is. it is here with the minus 1, that's 1, 0, 1, minus 1, 0, so it would be up, down, minus, down, up. This would be the analog of the single state, but you have all 4 of them, and you can play bare inequalities if you wish also with the other ones, even though the singlet is the most popular one for entanglement. Okay, and then the reverse operation. How to do it. So just this is mathematics, you play with bases. Now, the teleportation game is the following. The question, the problem, the task is the following one. Suppose that Alice has a spin, so let's think about the spin, so let's read if you want to speak in the language of quantum computation, in a certain state, alpha 0 plus beta 1. It's a generic state psi that Alice has. And the question is, can I teleport? So the idea of teleportation is more, so you say instantly, but it's not, we will see about that. So I don't know, I'm not sure about the origin of the word, why teleportation, not just transferring. Well, probably because teleportation is more catchy for the news. I want to transfer the state to Bob. How do I want to transfer the state to Bob? In a fancy way, not just carry the state to Bob, it would be very simple, just carry the state to Bob, but using entanglement. And in particular, Alice and Bob share, they share other 2 particles that they are in the entangled state. Now you can choose any of the 4 states, but we choose the phi class. So just to remind you, phi class, we choose this state here. Also because this is easier to create with photons. Singlet is better with the massive particles, that one is easier. Okay. So the total state that we are talking about is this one. So we have this, so Alice has, we call chi, C, the particle C, the particle that encoded in the state psi C, and then Alice has one of the 2 particles, and Bob the others, and the 2 particles A and B are entangled. No? 3 particles altogether. Alice has 2 of them, this one and one of the 2 of these, and Bob has the other one. And that's it. So again, it's some simple mathematics, so it's the cross product. Again, this is this state here, cross, the phi plus state is this one. And then, if you want to play some mathematics, just rewriting, nothing happens. This state here can be rewritten like this. What is the important difference in terms of what happens, if you don't know really the protocol, that in going from this line to this line, we have gathered together the 2 particles that Alice possesses. No? Alice possesses the particle carrying the state C and particle A of the 2. Particle B is with Bob. So this is the state of the particle by Alice. This is the entangled state of 2 particles, one with Alice and one with Bob. Now, this is in the superposition, and you can see this state in an equivalent way, and this is factorized. Now I give up factorization here, I scramble things, and this is a state of an entangled state of the 2 particles that Alice has, cross a particle for Bob, and then you repeat this story. This is just a mathematical thing. Nothing. But now the question is, so now suppose that Alice is capable, and we will see how, to perform a Bell state measurement. So Alice doesn't measure the state of one particle, but measures the state of the 2 particles together, of the particle Ca. So she has both particles, and she wants to measure the joint state. You can do that. We will show you later how. You don't have to always to measure just states of single particles. You can measure an entangled state of pairs of particles, or even more. So Alice, so basically, from the mathematical point of view, if you wish, Alice, instead, let me go, Alice, instead of making measurements along of observables that have these states as eigenstates, this will be measuring the state of the two particles, Alice measures an observable that has these states as eigenstates. Now it's AB. Here it's AB, and will be it's CA in that case. So you can have an observable that has entangled state as eigenstates. And so at the end of the measurement, you have the entanglement. Okay, so Alice makes a bell state measurement. So a state for the measurement of the state of the composite CA system. You see that in this state, there are 4 possible states. They have the same factor in front. So there is probability, so there can be 4 possible outcomes, with each with probability 1/4, equally distributed. And the outcomes are the pieces. So since these states are orthogonal, at the end of the measurement, the wave function will randomly collapse to this, or this, or this, or that. The final outcome is this one. No? I hope you are following me. Standard quantum mechanics. You measure, you get one of the possible outcomes, but then the collapse of the wave function brings also the rest. Collapses, everything collapses. And so it brings also the state of both with it. So the final state will be either this, or this, or this, or this. With probability 1/4, 1/4, 1/4, 1/4, 1/4. Now, given this, so, and this is the state of Bob. The Bob state is either this, or this, or this, or this. Now, the point is that Bob, can Bob do something to understand, to finish the teleportation protocol? The answer is, what can Bob do to finalize the teleportation protocol? Okay, and what happens?
Propagates. One of the propagates based on the measurement we get.
No. Any idea? The answer is in the previous theorem. What can Bob do to finalize the theorem? The answer is nothing. Bob, at this stage, Bob has no hope to do anything, because the previous theorem, the no signaling theorem, tells you that Bob can, whatever measurement, whatever action that Bob takes, he will get the same outcome as if Alice didn't do anything. So for Bob, practically nothing happened. So this is the situation, but the states are mixed, and if you do the mathematics, the statistics for Bob that coming out from this state is the same statistics that would come out from this state. So this is the state before Alice makes a measurement. This is the state after Alice makes a measurement. The physics of Bob here is the same as the physics of Bob there. Nothing happens, no signaling. So how does the teleportation protocol work? The teleportation protocol works. It has to circumvent this problem. Alice makes a phone call to Bob, because Alice knows what happened. Alice knows the outcome. So Alice makes a phone call, which means classical communication, which means subluminal speed. So the overall protocol is not instantaneous. It takes at least the speed of light for the classical phone call to go from from Alice to Bob. Alice makes a phone call to Bob and tells the following. Oops, to me. If, so, they're a bit out of focus, but you can understand. So if Alice gets the outcome phi plus, then it tells Bob apply the identity, which is which is a snob way of saying do nothing. Do nothing. You have already the state, remember? This is the state, no? Alpha 0 plus beta 1. If Alice gets this outcome, she tells Bob, apply Z. But he introduced the Z state. No? The Z state just flips the phase of 1. If you flip the phase, minus become plus, and you recover alpha 0 plus beta 1. If the outcome is this one, Alice tells apply the X gate. It's the NOT gate. Turn 1 into 0 and 0 into 1. And again, you will have alpha 0 plus beta 1. And then finally, if the outcome is this one, then Alice tells Bob, do both things. It's the Y gate, which is X and Z. So flip the phase and exchange the values. So in these cases, at the end, so after this phone call, with at least theoretical level, with 100% probability, with certainty, the initial state of Alice has been transferred to Bob. That's the teleportation protocol. Why is it called, why at the end of the day it's called teleportation and not transferring? Because the physical state, and that's where non-locality matters, and that's important. Because the physical state never moved continuously, so in a continuous manner from Alice to Bob. It didn't happen. Because of non-locality, Alice's measurement immediately changed things at Bob's side. That the phone call is, so to say, it's needed only for making order after the measurement. For telling Bob, look, giving Bob the instruction, look, this, do this, do this, do this, do that, in order to recover the state. But the state never physically changed from a place to another. So in some sense, it's like the teleportation of Star Trek in some sense. When teleportation, what is the idea of teleportation? It's not that the guy just, he said, beam me up to the spaceship. That the guy is lifted with the rope to the spaceship. The guy disappears from here and appears there. So it is something like that for the state. But you need the classical, it's probably like beam me up or that. You need a classical communication channel to record the final state. So in that sense, teleportation is a good word. It's a teleportation of the state, it's not a teleportation of matter. So that's another important difference. So it's not Star Trek in that sense. Alice has two particles at the beginning, Alice has two particles in the end. Bob has one particle at the beginning, Bob has one particle in the end. So if you want really to stretch out, and now it becomes science fiction, but if you really want to bring to the human side teleportation, how would teleportation work? That it's me here, and there is an equivalent amount of matter on the spacecraft. And then the teleportation protocol works in such a way that with many photons exchanged, the teleportation protocol destroys the state, my state. The atoms remain here, but they destroy the state. It's not the shape of my body anymore, it's just a mess. And reconstructs the shape with the piece of matter on top of the spacecraft. So, of course, it's science fiction. Impossible to do that. So just to give you theoretically an idea. So it's not a transfer of energy, it's not transfer of matter, it's just the state, or if you wish, the information about the state of the system that it is transferred. The only thing that is transmitted, so physically transmitted, that moves to the same space from one place to another, is the phone call, is the classical communication. The classical communication is classical, so it means that there is a little pigeon, just to make a joke, that flies from Alice to Bob with the information. But there is also an important thing about the classical. What is the classical information that is transmitted? The classical information is just two classical bits of information, because Alice has to give one of 4 instructions. 4 instruction means 2 bits of information. So the classical communication channel includes, is made only 2 bits of information for completing the protocol about an entire qubit. An entire qubit, in principle, has infinite information, because you have the phases here, the relative phases that are complex numbers, real complex, so it's a lot of information, infinite. So if you think of a block sphere, it's the direction, it's much richer information. First of all, so with 2 bits of classical communication, you transfer much more quantum information. But most of all, those 2 bits only contain the information about the operation that Bob should do, but not about the state. So there is no information about the state that is being teleported. And this is important for security reasons in quantum communication. The classical channel doesn't have to be protected. It can be eavesdrop, the classical channel, because it doesn't contain any relevant information about the state. Okay, so these are the points. Okay, so now let's see, just we see the thing, and then we are done for today. So in the circuit version, how do you do the teleportation protocol? So this is how you can generate the best state. So I leave it to you as an exercise, so that you learn from Vahid's lecture. H is the Hadamard gate, the gate that you know a bit of quantum computation, not just that use the basics. That creates the superposition. This is the control node, and then it's a simple exercise for you, if you wish, that with this simple operation you can create any of the best states, or the 4 best states. The one we use is this one. Okay, so the quantum, so it's not magic how to create a best state. It's not even magic how to measure a best state. The thing that I told you before when we were here. Now Alice performs a best state measurement. How can you measure the best state? It's a manual, so you have the 2 parts. Experimentally, I don't know, you also theoretically, how do you measure the best state? Let's see here, even the best state, it's very easy to measure. So these are the 4 possible best states. How do you know which one it was? Well, if you use this piece of circuit, so control node and plus Hadamard, you will see that you will have these 4 possibilities. If you get, and then you perform a Hadamard operation on the 2 qubits now, and control node, and then Hadamard, and you measure the state in the computational basis. If it's 0, 0, then the state was phi plus, our state. If it's 0, 1, was the psi plus, 1, 0, that's the phi minus, and 1, 1, the psi minus. So this is how you do a best state. And then with that, you have the teleportation protocol. That's it. That you find it in Google, from Google Images. So you see, the goal is to teleport the state psi from, so this is Alice, this is Bob. So from Alice to Bob. That's what we want to do. That's the teleportation protocol. So if you wish, you initialize the qubit of Alice and Bob in 0, 0, for example, and the first part you create the best state, the phi plus, or you can say that you have it already. So you can skip the first part. Then you make a best state measurement, and then, depending on the outcome, 0 or 1, you apply x and z to this state, the way I showed you before. And you have. You can go even farther, and you can do entanglement swapping. We did the last topic. Entanglement swapping. It's a very interesting. So this is the circuit of entanglement swapping. Do you know already about entanglement swapping? Does someone not know about that? You know. You don't know. So, who knows? So, probably it's not so easy to guess what's happening here. what's happening here, so in this circuit, basically you have to think of the following thing. That well, I'll show you later. So this thing goes as follows. So what is this box here? If you remember, H Hadamard gate plus control knot is the creation of a Bell state, a phi plus state, if you remember. So we are starting with factorized states. Now this means that we are entangling the first two and the last two. We are entangling. So the first two and the last two are entangled. Entangled, but factorized. So this block and this block are factorized. Two bells. Now, if you remember that this is a Bell state measurement, but between these two, the middle ones, this is a Bell state. And then you just a classical communication. So if you do the math, right now I don't have time now, but perhaps tomorrow we will see. The bottom line is this one, the bottom line. I mean, you see, it's very simple now. We have entangled states, entangled state. It was the first box in the previous slide. This one. We create two entangled pairs. Then we make a Bell state measurement. The outcome is that the two outer qubits, so this one and this one, the first and the last in the picture now, they are the one on the left and the other on the right, are entangled. So the entanglement was among these two particles, and because of the Bell state measurement, has been swapped, entanglement swapping, to the two outer particles. And this is the basic functioning of a quantum repeater, as the slide says. So you swap with measurements, you can move entanglement around. If you see the picture here, if you see from there, the first and the last qubit never talk to each other. There is no gate connecting directly the first and the last. Nevertheless, through the chain of connection, the first is connected to the second will be connected to the third is connected to the fourth. With the chain of connection, you can entangle the two outer part photons, typically, because you use it for communication, or to be any physical system. So this is a quantum repeater. What is a quantum repeater? It's a quantum version of a repeater. What does the repeater do? The repeater amplifies, in some sense, the signal. The signal decays, and then you want to have a repeater at some point that amplifies the signal in order to move it, it goes on a longer distance. The same happens with quantum communication. With quantum communication, also the photons, there could be a photon loss at least. And photons die after some time on the optical fiber. You want to have a repeater. But you don't want to have a classical repeater. Classical repeater means, in the quantum language, means that you read the state and you copy it. You can do that. You become no-cloning theorem. So you have to preserve the quantum state. And that's how you can do that. These two entanglement, so this you can consider this a physical distance. You have entanglement over this distance. With this trick of entanglement swapping, you pictorially say you double the distance over which you are entangling. So now you have entanglement over a longer distance. Not because the particle, so you see that none of the particles travel the long distance. The particles travel at most distance d, but the state now is shared over a distance which is 2d. Or if you put the sequence of quantum repeaters, you can double again and again and again, and in principle you can go any distance you want with quantum repeaters in transmitting entanglement and so quantum information. Okay, so this is the end for today. Tomorrow we will go to the last topic, that is cryptography. But I hope that so you can see that this nice pattern, these fundamental questions that set the physical ground and physical mindset and the mathematical tools for developing something that now is useful for technologies, for quantum technologies, in particular for quantum communication. Most striking for me will be QKD, as also I anticipated, the possibility of securing information in an unbreakable way, thanks to the quantum. Okay, thank you.